Have you ever wondered how your bank decides if you'll get that loan? Or how your email magically knows what's junk and what's not? Well, the answer often comes down to this really powerful tool called logistic regression. It's basically the engine that takes a whole mess of data and turns it into a simple yes or no. So today, we're going to lift the hood and see exactly how it works.
Okay, so here's our game plan. First up, we'll look at why a simple straight line just doesn't cut it for these kinds of questions. Then we'll get into the super elegant S-curve solution and the language of odds it speaks. After that, we'll jump into a real-world example, predicting diabetes. Then figure out how to tell if our prediction is any good. And finally, we'll see why this whole thing matters so much in our everyday lives.
All right, so first things first, why do we even need a special tool for what seems like a pretty basic two-choice question?
Okay, put yourself in the shoes of a health researcher for a second. You want to know if age can predict whether someone has diabetes. Now, the answer can only be yes or no. It's one or the other. In the world of data, we call that a 1 for yes and a 0 for no. So what happens if we just try to draw a regular old straight line through that data?
Now, a straight line is awesome when your data kind of follows that trend, right? But with a yes or no question, all your data points are stuck down at 0 or way up at 1. And if you try to force a straight line through that, well, the line's going to keep going. It'll go below 0 and way past 1, and that's a huge problem. I mean, how can you have a negative chance of something happening or 130% probability? It's impossible. We need something that respects the boundaries.
So yeah, the straight line is it's out. It's not the right tool for this job. We need a different shape, something with a little more finesse.
And that's where logistic regression steps in. It is built from the ground up to connect things like age or income to what's called a dichotomous outcome. And don't let that fancy word scare you. It just means the result can only be one of two things, yes or no, 1 or 0. So instead of that runaway straight line that flies off into impossible territory, the logistic model uses this really beautiful S-shaped curve. You can see right away why this works so much better. The curve is naturally squeezed between 0 and 1. It never goes below and it never goes above. It's the perfect shape to talk about probability, which, as we all know, has to live somewhere between 0 and 1.
Okay, so how on earth does the math actually create that perfect S-curve? Well, it's pretty brilliant, actually. It does it by taking a little twist on how we usually think about probability.
This is where it gets really cool. The model does this clever little three-step dance. First, it starts with probability, just like you'd expect. But then it converts that into something we call odds, which is just the probability of it happening divided by the probability of it not happening. But here's the magic trick. It then takes the natural logarithm of those odds, and that gives us something called log odds, or the logit. Now, why do all that? Because the logit can be any number, from negative infinity to positive infinity, and it has a straight line relationship with our data. It's a clever workaround. The model gets to use the simple straight line it's comfortable with, and we get a final answer that's always a perfect probability.
I know log odds sounds kind of weird and abstract, so let's make this super concrete and look at a real-world public health study that's trying to predict diabetes.
All right, what you're seeing here is the actual output from a logistic regression model. Now, don't worry about all the numbers, just focus with me on that estimate column. We're trying to predict diabetes using just one thing, a person's age. And those numbers in that column, those are the coefficients that make the whole model work. The key number here, the one for age, is 0.0511. So what does that even mean? Well, it tells us that for every single year someone gets older, the log odds of them having diabetes goes up by 0.0511. Now remember, this isn't the final probability just yet. It's that special in-between number that the model thinks in.
And this is where we get our payoff. We can take our model, plug in a specific age, let's say 50 years old, and then run the math backwards from log odds. And when we do that, we get a clear, easy-to-understand probability. In this case, the model tells us a 50-year-old in this group has an 11.5% chance of having diabetes. It's a specific, concrete prediction.
But, making a prediction is one thing. Making a good prediction, that's the hard part. So how do we know if our model is actually any good? How do we grade its performance?
And this step is absolutely crucial. We have to ask, does our model actually work? In our example, can it really tell the difference between people who have diabetes and people who don't?
So statisticians have a great tool for this, and it's something called an ROC curve. You don't need to worry about the math, just the main idea. It basically gives our model a grade on how well it separates the yeses from the nos. A score of 0.5 is a total fail. It's no better than flipping a coin. But once you get above 0.7, your model's starting to be pretty useful. Hit 0.8 and it's excellent, and if you get above 0.9, your model is truly outstanding at telling the two groups apart.
Okay, so we've got this amazing tool that can predict a yes or a no, and we have a way to check its work. So where does this all matter? Well, it turns out it's pretty much everywhere.
I mean, seriously, this technique is hiding in plain sight. Your doctor might use a model like this to estimate the probability of a disease. Your bank for sure uses it to figure out the odds you'll default on a loan. It's running right now in your email, deciding what spam. It's behind the ads you see, predicting if you'll buy something. It's even used in politics. Basically, anytime a big decision comes down to one of two outcomes, logistic regression is probably the engine making it run.
So, look, we've seen how this incredible method gives us the power to predict a simple yes or no, and this tech is only getting better and more accurate. So the final question, it isn't really about the math anymore. It's about us. As we get better and better at predicting things, from our health to our behavior, we have to start asking ourselves, what are the most important questions we should be trying to answer? And, maybe just as important, which ones should we leave alone?